Okay, put your thinking caps on because we're going to talk about some cool stuff in this video. The first thing we're going to talk about is the area of a trapezoid. So let's draw a trapezoid. So a trapezoid is going to be something of this nature that has two parallel sides, but then this side here and this side here is parallel, but these two sides are not parallel. That's going to be a trapezoid. And what we're going to do is simply, to get the area of this trapezoid, is simply divide this thing into two triangles. And you will see here that the height, let's say, of this triangle here has a height of h. But if you look, that also the triangle, this other triangle here, has a height of h. That is the height from here, the perpendicular height, to the height that side reaches is h. So if we call this side B1 and this side up here B2, so we get first this triangle, and that color there we have the area is 1/2 base 1 times height. And then let's do this triangle plus 1/2 base 2 times the height, and we get the formula for the area of a trapezoid. We get the area equals, we can pull the 1/2 h out of both of them and get 1/2. Well, let me write it like your book does. It pulls the 1/2 out on this side, and we're left with B1 plus B2 there. So I pulled the 1/2 out, and now pull the h out on the other side. So 1/2 base 1 plus base 2 times the height is going to be the area of a trapezoid. Okay? Now let's talk about stretching. So let's draw a square here. And so this side has length 2, this side has length 2. And let's say we multiply this bottom side, we extend it by a factor of 3. So we're going to extend it to 6. So let's move 1. So 3 times 2 is 6. And we extend the, well, let's just leave that piece alone. So that is, we now have a length on the bottom of 3 times 2, which equals 6. Right? 1, 2, 3, 4, 5, 6. And so this area here was 4. 2 times 2. What's the new area going to be? If we look at the new area, it's going to be, so the area of this one is going to be, the area inside here is going to be what? 1, 2, 3, 4. 4 times 2 is 8. So my total area, is going to equal 12. Oh. So note that I multiplied the original area, the original side of 3, I stretched it by a factor of 3, and I didn't stretch the vertical side there, I only stretched the horizontal side. So if we look, it increased our area 3 times 4. That is, when I stretched by a factor of 3, I actually stretched my area by a factor of 3 as well. Let's assume, what if I'd stretched, what if I'd moved this up? So if I added an additional 1 to 2, what would I multiply 2 by to get 3? 2 times what? 3/2 equals 3. So that is, if I stretch the vertical component by a factor of 3/2, let's see if we're going to get our new area. I'm going to bet that it's going to be, we stretch by 3 on the bottom and we stretch by 3/2 on the top, and our original area was 4. And so what's that going to give me? 3 times 3 is 9, times 4 is 36, divided by 2 is 18. Okay, so I stretch by a factor of 3/2 on one side and a factor of 3 on the other side, and I multiply by the original area and I get 18. So let's count it. Here's 8, here's 4, so that's 12, there's 13, 14, 15, 16, 17, 18. So again, we have 12, 13, 14, 15, 16, 17, 18. So that's going to be what you read in your book called the Stretching Theorem. That is, if you stretch an area vertically or horizontally by h and vertically by v, and it had an original area of a, then the new area is going to be h times v times a. And the reason this makes sense for things that aren't even rectangular is because you'll find in calculus, even when you have, say, a circle, you can approximate it with a bunch of little rectangles. And if you make those rectangles smaller and smaller, you can get better and better approximations, and that's when you're going to get into something called the limit. Okay? So that's going to be the basic ideal, is to stretch something by horizontally by h and vertically by v. If we know the original area a, the new area is simply going to be our stretch there, h times v times the original area. And that is where they get that stretching theorem. How much time do I have? 7:37. I think I'm going to end it with that one, and we're going to use this ideal of, we're going to use the trapezoid, and we're going to use this idea of stretching in the next video to try to derive a formula for the area of a circle. So that one's going to be fun. I'll see you there.